And it's essentially the announcement of the prefix to another network, to another common system. Pretty much saying, I am willing, I announce a path to a prefix. Announce a prefix. But the announcement is made to another autonomous system. And then the route, then B may want to announce it further. So in this way, information propagates. If B is connected to network CBE, it may make a decision to announce this path or not. That becomes a policy. So it's a selective decision on which advertisements to make and also which advertisements to accept. Like this, B may receive the advertisement but may not import it. Meaning that B does internally not advertise a path to this network via this autonomous system state, which also would be a policy. So that's so what we have is we have BGP interactions, called BGP sessions, between autonomous systems, but we also have multiple BGP routers within the autonomous system. That's called an internal or IBGP session. And the thing to take away from this is what the internal information each router must have in the same autonomous system, must have a consistent view. So they essentially need to find a way to disseminate everything that everybody learns. If this one learns something, it has to disseminate. And it has to be done in such a way that we don't create multi-hop paths within the same autonomous system. Alright, so then we got into more into the mechanics of how these BGP update messages look like. So we were talking about three attributes here. There are many more, but these three are essential. One of them is the origin attribute. If somebody advertises a prefix, it includes always the origin, which means pretty much tells you in which autonomous system to say origin 1 with this prefix. That means this prefix is really contained, owned by autonomous system 1. So you have some kind of ownership. In this way, you can then make a decision. Do you want to advertise? The second one is the path attribute. The announcement for a prefix always contains information on the path that is taken. Autonomous system path 2.1. Essentially, the announcement has a record of the autonomous systems that are traversed. The last attribute, where we ended yesterday, was the next hop attribute. This is now where an announcement is made to autonomous system 1, the router here makes an announcement to 8x3, and it puts its own interface. They are saying, well, I'm advertising to you this network, use this as the next hop address. That's how you can reach it. So that this router can then say, create a routing table entry 128 at this network destination 10.0.10.24 can be reached at next hop 128.111.1. That's in the routing table entry. That's at least enough to create routing table entries. The routing table entry always has this form. Destination network is 10. We have 0.1.0, 0.1.0/24. You then need a next hop address. If you're saying, well, use this address as next hop address, then this router here can then use 128. 111.1 as the next hop address, and then if AS3 makes the announcement, this router here will announce the interface that can be used. But the real picture is a little bit more complicated because this is an autonomous system, not a single router. Yeah? And so what has to happen now is that if you get in this next hop announcement, that you're really dealing with an autonomous system that has many routers. Many routers, which most of those don't even know what BGP is because it has not been turned on. Most routers, you will see exactly 3 routers that understand BGP. The rest, 30, 50 routers, don't know what BGP is. It has not been turned on. And they're running just the internal route. They know how to reach all routers. Yeah, that's what an IBGP and an IGP and an intra-domain routing protocol does. An intra-domain routing protocol, IGP router stands for OSPF or RIP router, internal gateway protocol. Router knows how to reach all routers within the autonomous system, but it doesn't know anything else. What it knows is this router knows something about this network here. Because this network here is kind of the IP address of that network. This is an internal router still attached to it, so that information is still propagated. So now, the critical question is, how is the IGP and the EGP, the intra-domain routing of OSPF and the inter-domain routing of BGP, how is that stitched together? In the end, it all has to be mapped into a routing table. So this is illustrated here, and it's also done with the next hop attribute. So let's suppose, so this is an autonomous system that makes an announcement and saying in advertising 10.0.121, advertising as next hop 128.111.1. That's this address. Now this advertisement is received by autonomous system 3, received of course by a BGP router. That BGP router receives now, that BGP information is now passed to all other BGP routers via an IBGP session. Now this router here is the exit router. This one talks BGP, this one talks BGP. So now the router 1 receives as next hop information 128.111.1. The issue here is router 1 is not connected to this network, so it cannot directly, it is not connected to this interface. It doesn't have a link. So somehow what has to happen is router 1 must figure out to send anything that is going into this destination network to a router that's on a path that somehow gets the packet to this router here who is connected to this interface. Yeah? And that's what's happening next. So essentially what has to happen is the BGP information, yeah, next hop is 128.111.1, has to be this destination. Has to be mapped into a routing table entry for that address. And this is how it's done. Yeah? So the router receives this message. Then it says, well, I know about the network 128.111.1, which is this network here. Because router 1, this is router here on the left one here, let's say router 0, advertises its interfaces internally using BGP. Now this is just the external, but it's still one of its connected networks. So this information is floating, and for that, for this one here, for this network, it has a next hop address. It's this router. That has been configured by IBGP, and so does this router here. So now what it does is it now creates. So it has this routing table lookup. Now it says, well, to reach the next hop, I would pick this routing table entry and would have 192.0.1.2 as the next hop. So it takes this and, well, that's the way how I reach network 10.0.1.0. So this BGP attribute here leads to the creation of a routing table entry at router 1. That sets it on an internal path to set it on a path that reaches then a BGP router, which then can deliver it to the other autonomous system. So that is how IGP, intra-domain routing, and inter-domain routing are stitched together. Yes?
So router 1 and router 0 are not directly connected?
They're not directly connected. Yeah, this should actually be a dotted line. It indicates here they're running, they are running an IBGP session, so they have a TCP connection between them. That TCP connection goes across the entire end of campus. Think about this one here being in Mississauga, this one here being in Scarborough, and now they're setting up a TCP connection between them. In that sense, the TCP connection connects them, but it's going through multiple routers.
So router 0 uses a TCP connection and then advertising to router 1.
Yes.
Saying that if you want to reach 128.168.1.1, you can send it to me. So how does R1 know that it has to send it to 192.0.1?
Well, router 1 has this routing table entry. Yeah? So it knows that if it gets something for this router, it knows everything internal. So it knows this is something that the Mississauga router is connected to, so I know my next hop. This is done by OSPF. Using now this BGP information, it stitches this together to create this entry. Okay? Now, for the route selection, so what we've seen is in this example here, kind of the way this is done is advertisement. So what happens is an autonomous system receives multiple advertisements for the same path. That's typical. If you have multiple connections, you're having a network like a tier 1 network service provider that has access points throughout the world, connections throughout the world, points of presence throughout the world, service locations. Then these service locations receive advertisements from all over. So a decision needs to be made. If multiple advertisements are received, this one here should be a different autonomous system. So this, let's say this AS0 here, it receives. So AS0 here has to make a decision which neighbor to pick if it receives the advertisements to the same network. Now, BGP has a whole bunch of criteria to make that selection. The top level is the highest local preference. That's an internal set parameter. That's something that is set in the configuration, saying if pick AS4, highest local preference. Now, not pick AS4, send it out on this interface. The second one is to use the shortest AS path. That means the AS path is the number, the AS path is the number of autonomous systems that are traversed. Take the shortest one. That's the second criteria. The third criteria is this metric. To be honest, I don't know what it means. Because multi-access discriminator is for multiple. So I don't quite know how these two are distinct. So this is also internally configured. Prefer IBGP over eBGP routes. So if an advertisement is received, you prefer the announcement that was advertised internally. This is something comes together. Yeah. So if routes come in, they are all internally advertised, and these are the paths that routers prefer, preventing somewhat that routers, if they receive multiple announcements, if they prefer the internal announcements, then pretty much the decision is left to the internal autonomous system. If you had it the other way around, then if you receive an update for a network here and here, you would always pick that. It would be difficult to define a uniform routing policy. If you're saying, pick the IBGP session first, well, then that internally can be set then as a policy, in particular if it is centralized, controlled centralized with a router factor. This one here, the fifth criteria, is pick the lowest IGP cost to leave the autonomous system. That's an interesting one. This results in a routing, in a way that BGP routing creates something that is called hot potato routing. Hot potato routing is exactly this. You're touching a hot potato, just trying to get rid of it as quickly as possible. Now that has a very interesting effect on path in the network. So the question is always, if you are having a path in the network, trace route from A to B, making a trace route somewhere to California from here, how about the path back? You would assume that the packet travels the same path back. That is generally not the case. The reason for that is the hot potato routing rule and kind of this pick the lowest IGP cost to leave the autonomous systems rule in BGP. Yeah. See, this is a routing criteria which is 5 steps down, creating an effect that many paths on the internet, long paths on the internet, generally have a different path in both directions. Which is not that easy for traffic engineers. Yeah? I send my TCP, my data goes in this way, the acknowledgement travels a completely different path. It's not going on one link. The last one is just a tiebreaker. Everything else fades in, and they have to make a decision. Yeah, the lowest router ID. Yeah, that's just a random. That's whatever the next one. So let's go through this. Well, so the local. I discussed some of these. The local preference is just something. When you get multiple points, then internally you're having your contract, you have the customer relationships. The autonomous system one then defines, well, I have local preference for this one is 80, 50, 10, 100. So you pick the smallest one, that's your biggest preference. You pick the largest one, whatever it is. Yeah, this value is set internally, which means I'm connected to many networks. One of them is my service provider. That's the one. If I get routes advertised from there, those are the ones that I pick. Hot potato route. So this is the rule. So we have 2 routers receiving advertisements for, these are prefixes. Prefixes are like 10.0.1.0.24. Both being announced. Now they arrive here at the IBGP session here at router 3. So router 3 gets 3 announcements. Which one does it pick? And they're both announced. If it has an internal preference, that's fine, yeah. If you have this value set here, the local preference, that is set, no issue, yeah. But if it's the same thing, so the rule is that router 3 should pick the route that has the shortest path to reach the exit. Yeah, so if this path here has an IBGP cost, so this is the cost of the shortest path cost, the OSPF cost, or the RIP cost. If this is going to router 1, has cost 6, and going to router 23 has cost 23, it picks the one that is shortest. So makes sense. You have to make a decision. You pick the shortest route. What's the rationale? Well, this being the routing policy in here, OSPF, this means it's relatively close. Pick this. That's good. Yeah? But what it really means is the client router, the autonomous system A, does everything possible to get rid of this packet to network X as quickly as possible. That's the hot potato. I have a packet. This one here I have to carry longer, because 23 could mean a different things because these link metrics are defined. In generally, there's this relationship between the number of the length of the path and the cost. In RIP it is directed. Each hop has a cost of 1. 6 means I go, the path here from here to here goes through 6 routers. The path from this BGP to this BGP goes over 23 internal routers, even though 23 in RIP does not go. Alright, so the hot potato routing has an interesting effect. Let's look at these two networks here, autonomous systems. Let's think about them as this one being a Canadian-wide network here, this being the East Coast, this being the West Coast, this being the United States, America network. Yeah? West Coast here, East Coast here. So we are here in Toronto and somewhere way here in San Francisco. Or let's put it this way. Yeah, San Francisco. Or let's say this is Ottawa and San Francisco. This is much better. This one here is a location on the East Coast, like Toronto to Chicago. There's a very high density. Vancouver, Seattle. Vancouver, Seattle. So we now have traffic going from the traffic between A and B. If this host here sends packets to the destination here in San Francisco, well, which route is being picked? Well, it picks the one, sends the packet on the East Coast to Chicago, where it's traveling in. Let's say this is Bell Canada, this one is AT&T, going in AT&T network to traveling through the entire United States. If the packet is sent back, the solid route in San Francisco picks its shortest route and possibly sends the packet over here, where it's traveling then in Bell Canada. Yeah? So kind of what is the philosophy behind that? Well, Bell Canada does the right thing. It gets the packet out of its own network as quickly as possible and makes it the destination route to carry the packet. And this one here makes the same thing. So now we're sending packets. Yeah, we're just sending a ping. The reply packet goes this way. That's the effect. Now, this is just a phenomenon. The network is, if that's how it is, that's how it is. One can live with it. However, this customer here, this is a customer in this network, a client of Bell Canada, has paid Bell Canada a lot for a high-speed service. So it gets high-speed service, but in this network here is provisioned to support this customer. They're saying, well, it's my network here. But no, with this routing policy, even though you're being paid for having top-tier service, the routing policy is such that the traffic from Ottawa goes directly, goes as quickly out of the network, out of Bell Canada's network as quickly as possible. And here, there's no control over what service is provided or not. Do you see the thing? Yeah. So that's hot potato routing. Yeah, so very much. This is all. Yeah, we have a couple of more things on BGP. So that's the general idea, how it works, how routes are picked, how routing tables are set. So for BGP, yeah, so BGP messages have to do with policy. This updating the routing table is one of the things that are done. BGP update is received, so there are import rules and export rules. Import rules means which advertisements do I accept. If I accept an advertisement, if this system, so this is the BGP routing process here, if you receive an advertisement, that essentially means your outgoing traffic is going to go that direction, because you now internally accept the path, set your routing table, so whatever has been advertised then ends up in the routing table for that path. So these are the import rules. Export rules say if you're advertising a path, that means you're willing to carry all traffic for that announcement. This is a big cause for problems with BGP. If some small service provider is sending out false advertising. Things happen where you're making an advertisement where a small ISP all of a sudden makes an advertisement for Google or for AT&T's network. That means that this small ISP all of a sudden changes all the routing tables and pretty much has all of AT&T's traffic directed to itself, of course creating havoc. These things happen, and there are people at AT&T, they would notice this, there's some network traffic not going where it's going. They do this by phone calls and emails. They fix it. Tell that ISP how to set up the routing table, what to do, what not to do. How to change, it's essentially change export rules and import rules. And that's what's being done. Let's see, so rules come in, then you're having your multiple announcements, you have to pick one. These are the criteria that we went through. Yeah? Local attributes, shortest path, shortest AS route, hot potato routing, what have you. Then the routing table is updated, we have to adjust this part, and then you make a decision is made whether a route is advertised. That's good. So, import, after we discussed. Yeah, so the import and export rules determine how much traffic is going through this network and where it's going. So the thing is, if you want to control your inbound traffic, you have to change the export rules. If I export a path, I get the traffic that's going in that direction. So that's how I control the inbound traffic, changing the export rules. Likewise, if you want to change the outbound traffic, want to go traffic from here going out on this interface or not, that is then done by modifying the import rules. If I don't import a rule that advertises AT&T's network, if I don't want to have the traffic to AT&T's network go through this router, then I should not import an advertisement for AT&T's networks from here. That's what's done. Alright, so that's done. Now, back to routing policies. Yeah, so this import-export, that is how policies are defined. So now if you're having a network here of autonomous systems, these are now the relationships that we had earlier. We had peer and customer-provider relationships. So now we know how routing policies should be implemented. So one thing is, look at AS5 and AS3. AS3 is a peer network. It's a transit network. AS5 is a multi-home stub network. They all both talk BGP. They're just sending out update messages. How do they implement policy? Well, AS5 as a transit network, as a stub network, it's a multi-home stub network, should never advertise any path that has been received from somebody else. AS5 receives advertisements from AS5. These advertisements should never be exported to anybody else, because if AS5 exports an advertisement which of a route that has been received from AS1, well then AS2 may send the traffic in this way. Just done through this rule. You see this? It's kind of, in the end, it boils down to something very, very simple. Likewise, this rule that peers do not make transit for other peers. So remember this one? Peers take traffic from their customers and carry traffic to other people, to the peers' customers, but they don't make transit for others. It's also done by just a routing policy that if AS1 receives an advertisement for when AS3 learns about the path AS1, AS4, it does not pass this on to AS2. It passes this on to AS6 because AS6 is a customer of AS3, and AS1 is a customer of AS4. However, AS3 does not pass this path here, AS4, AS1, onto AS2, because that would then make AS3 transiting, making transit for this peer network AS1. Yeah? Because AS2 is not a customer of AS3, AS3 should not export an announcement that it's elsewhere. That's pretty much as simple as it is. That's how these customer and peer-to-peer relationships, they're just realized through these announcements. All right, let's see. Maybe this is not interesting. Short AS path. Yeah, the length of the AS path, that was the second criteria for making a routing selection. Now, short AS, short number of autonomous systems on the path, does not mean that the route is short. And to illustrate this, because essentially, if you're getting an autonomous system, you don't know how many routers are being used in that autonomous system. You can find out by trace route, but BGP doesn't do that. So what you can have is, if you have now a path between AS1 and AS6, if you're getting the shortest AS path, yeah, you're getting both advertised. But this path here to a route over here would be AS1, AS3, AS4, AS5. From here it would be AS1, AS2. This one is the shortest, this one you pick. But if we're actually counting the number of routers, it could be a different picture. Yeah, two different moves. That's what I'm saying. The view of the router and the view of autonomous systems does not really, is not necessarily is aligned. That's what I have in mind. Well, we talked about BGP routing table growth. This one here is an interesting one because you've seen an earlier one. The routing table growth. Look at this, 1993. Yeah, it has a few thousand routes. 2001, the routing table size is 100,000. Today, routing table sizes of BGP routers. Yeah, so now you know what when I said in the core of the internet, routing table sizes. That's what I meant, BGP routers. BGP routers must have a global view. Today, so this is a plot from 2010, and one lecture I gave you the one from 2011 that just got cut off, so this is one from last year. So we're right now, I think, closer to 400,000. So now the routing table sizes are 300,000 applications. That's a lot of routing table entries to look through for each packet. That's what the routers have to do. Using fast lookup algorithms. Yeah, so that's what's taking place. Now, BGP is so large. Just you're connecting essentially all BGP routers off the internet. They are running kind of one large routing algorithm. So you're having roughly 50,000 routers, BGP routers, building one distributed algorithm, complex. BGP is known to have problems. It is known to no longer converge. The routing algorithm does not converge anymore, meaning that there are changes faster than the routing takes to stabilize. There's actually a term for it. There's actually no translation for this. I don't know what the bogon routes. Bogon routes are bogus routes. Routes being advertised that don't exist. Unallocated IP addresses. Nobody knows where this is coming from. 10% of advertised routes are said to be going to black holes. They're going to anywhere. They're not going to anywhere. That's actually connected to this bogon, yeah? a large number of routes lead to a nonsense routes. Because you don't have traffic to these nonsense networks, but they're still being advertised. What you will also find, BGP is used, actually abused, but actually very useful, to implement services like Anycat. So this is the thing that when we learn about name resolution, DNS. DNS has 13 root servers. 13 root servers. Oh, 13. This is the top tier of when you make a name resolution. Essentially, every time you go to a .com, you will contact a root server, unless it's cached. Now, these servers are duplicated all over the world. So now what you're having, the same root server being in different locations. The same root server having the same IP address. All computers that you have the IP addresses of these DNS root servers hard-coded in a file. Now you have, if all computers would go to the same 13 servers, no matter how big that data center would be, it would be congested. Would also be vulnerable because of an attack. So now you're having these servers with the same IP addresses being in different locations. How is it done? It's done using BGP. Yeah? So you're essentially making advertisements for the same IP address that only reach to a certain radius. And then this is then, you advertising in South America, you're advertising root server A, DNS root server A, from somewhere in Buenos Aires, and the same IP address is advertised from Paris, and if the announcements never collide, they're contained, then traffic is going in this way. So there's a lot of stuff being done that is burdening the process. Yeah, so BGP is a simple protocol, difficult to configure. There are not many people who it has a lot of stability issues. There's many temporary loops. It's a tricky thing to configure to avoid loops in the IBGP and eBGP session interface. Yeah, so what I said is 39,000, roughly 50,000. This should be probably updated. How many AS numbers are allocated now? Just to give you a sense of how a tier 1 service provider. Yeah, so I picked this one. This is kind of a cogent. This is an ISP, tier 1 ISP. Yeah? So what they have is, this is the one that carries the traffic of U of T into the commercial backbone, into the commercial traffic, so the non-research traffic of U of T. U of T has somewhere 300 megabits per second of that type of traffic. So cogent, this would be kind of it's an AS, this is their network. That's kind of typical for an ISP. Okay, so the resolution is off. You see, so there are. So this is better. Yeah, you see the map. So they're serving parts of Europe and North America. They do have a point of presence, several points of presence in at several points of. So this is what they advertise. Stretches. So then, 60,000 miles of fiber. Connecting to 3,650 autonomous systems. And so this autonomous systems, called cogent, is connected directly to 3,600 other autonomous systems. That is for tier 1. They are in the center of it. All tier 1 service providers are directly connected. So they are really in the center of things. So they are. Let's see, what else can we look at? The service locations. Yeah, so we can look at. Let's see. I wanted to see if they have service location here. In this search vector. That's what I wanted to do. Okay, so we can take Toronto and can look at the we're looking at carrier neutral data centers. Carrier neutral data centers. Well, these are these carrier hotels, these internet where the internet exchange points are. So this is where they're located. Yeah? So they have locations in 151 Front Street, Equinix STD Connections. Equinix is very likely this is one of the IXPs. Then they have a location on the Toronto Stock Exchange. And there is another location, they're all in downtown. Yeah? So this is where they have, what this means is they have a service location, they have a router located there. Yeah? This building here probably has, I would say, several $100 million worth of telecom equipment. Yeah? So if that building goes out, Canada does not have telecommunications. Maybe the military and some wireless. Yeah, but pretty much all connections. You know, it's really the center point of communication. And you can imagine what they have as backup. They have backups with backups. So that's this. So let's maybe look a little bit at kind of what they are offering in terms of services. So this is what an ISP offers. And I said in Europe, we offer, we have SLAs, service level agreement. These are the contracts. These are now monetary contracts. This is people signing, this is the contracts between companies to carry traffic and between clients and customers. It's called a service level agreement. It says what is the kind of service that is provided. And this is what a service provider process. We're promising a packet success rate, meaning a drop rate of 1 minus this, so it's 0.1. We guarantee to have 1%, tenth of a percent, so 1,000. That's probability is 999 for successful delivery. 1 of 1,000 packets can be dropped. Let's see, the latency that is being advertised. So they're making a latency between intra-Europe, North America. As average backbone latency, they're selling 45, less than 45. This is what they're accomplishing here. Yeah? 40, just not much less, but this is what they're delivering. So these are the contracts. Okay. Yeah, and then we could have a look at their service level agreements. There's something to be learned. I mean, this is all now contractual speed. This kind of what this service is. So they say how fast they're installing things. We have T1, E1, T3, E3. These are just 1.5 megabit, 45 megabit. OCX, this is a multiple of 50 megabits per second, where X is the number and the multiplier. They're saying how fast they get the service installed. Then they say they have their latency in the contract. We have 4 dedicated internet access customer only. The monthly average network latency for packets carried over the cogent network between backbone hubs for the following regions is a specified below. That's the service contract that is being made. Then the packet delivery guarantee. Yeah. So they specify the average packet loss rate for the preceding 30 days. 0.1%. they're violating the service credit claim process. So this is the contractual side of the internet, between service providers. Now, this then gets translated into BGP rules. Let's do quickly that. It's actually my site here. It has a link here to the connected autonomous systems. So it has here a map. Shows a map. The map is not very interesting. Yeah? So it, we can go to the database that shows, this is the database, that shows now the connection of the cogent backbone to other autonomous systems. And so it says, yeah, so this is now code export from AS26, except any, from AS20, announce any. Announce, export, except import. This is BGP speak, yeah? And so this is the list. What was the what was the AS number of Toronto? You know it better than I do because you just did it in the pre-lab.
Was it 611?
Yeah.
No.
611?
That's for you off T, yeah. For you.
613? No, 1613. 613. 24 matches. See, several thousand is a lot. Yeah, you're typing in 611, you get multiple matches. 611, 6611. That's 20. We're going to put these into the 29,000. That's not.
Let me search AS611. That will.
611, not 611.
549 maybe? The 549 that I see there.
549?
Looks familiar.
239.
You still have the 611.
Yes, yes, thank you.
Oh, 549 is York University, I think. GTA networking. York University.
I think 239.
Given the fact that
Oh yeah, 239 is University of Toronto.
239. Thank you. All right. Find it. Oh, it's been searching for a while. Maybe find it by 10 times. Oh, no, okay. Well, essentially, it has to boil down to this. Yeah, so this is the link. BGP is critical in that this is where the routing protocol side, the architecture of the internet, the layout, the federation of networks, and the business of carrying traffic all intersect. That's the crucial piece. Yeah? All right. That's it, what I have on BGP. So the next chapter we're going to open, starting tomorrow, is about transfer protocols. Really, most of that will be digging relatively deep into TCP. Now you want to get away from here from a good understanding of what TCP does, and the lab, the TCP lab starts then next week. Is that right? Kind of keeps you busy, yeah? It's always something, isn't it? It's good for you, yeah?